isomorphism theorem gives a relationship between the certain ideals in R and certain ideals in R bar. And it says there is a bijection between, on the one hand, ideals J in R that contain I. So we'll put them like this. Ideals of R containing I. And they're in bijection with the set of ideals J bar of R bar. So you get all ideals of this quotient ring by taking ideals of R that contain I. I'll give you that bijection. And the bijection goes like this. To a J, we associate the image of J in R bar. And we're going to see that that's an ideal. And to an ideal J bar, in R bar, we associate the pre-image of it in R. And we're going to see that's an ideal that contains I. So there's an important bijection. That's like the bijection between subgroups of G containing a normal subgroup and subgroups of the quotient group. Same kind of bijection. And moreover, the quotient of R by J, this ideal containing I, is isomorphic to the quotient of R bar by J bar. So you get the same quotient rings. So this is like many of these very general theorems, the isomorphism theorems, it's more or less a tautology once you figure out what is actually going on. So let's check a few of these things, and I'll let you check the rest as you go through it. So let's see that this f of J is an ideal of R bar. Well, you have to check that it's closed under addition and multiplication from R bar. So let's assume that, so we have f of A and f of B are elements in f of J, where A and B are in J. Is there some in f of J? Why? Exactly. Then f of A plus f of B is equal to f of A plus B is in f of J, because the sum of these two things is in J. That's what I mean by tautologous. But the next one's a little tricky. Suppose f of A is in f of J, and that we have an arbitrary element, R bar, is in R bar. Is R bar times f of A in J bar. In f of J, I'm sorry. That's the point you have to use. And this is not true for an arbitrary homomorphism. You see, this happens to be a surjective ring homomorphism. Since f is surjective, we can write R bar as some f of R. And having written R bar as some f of R, we write this as f of R times f of A, which is f of R times A, because f is a ring homomorphism. And this is an element in J, because J was assumed to be an ideal. Very good. But if we didn't have a surjective ring homomorphism, then you just can't take f of an ideal and get another ideal. Be careful about that. Okay? For example, f of R might not be an ideal. Let's just show you that. I mean, so this is a warning here. If f is not surjective, f of j need not be an ideal. So you don't have an obvious map if you have, so for example, if you take the integers and you include them in the rational numbers, that's a ring homomorphism. Not surjective, of course. If a perfectly good ideal of the integers is z. If you take f of z, you get the integers in here. That's not an ideal, because the only ideal of the rational numbers are 0 and q. It's a field. Okay, so you needed the surjectivity to be able to write this r bar as f of r. However, the pullback works in any case. Whenever you start with an ideal here and you pull it back, you get an ideal in R. I'll let you guys prove that. But notice that this certainly contains I. Because I is f inverse of 0. That's the definition of I, because this homomorphism has kernel, surjective ring homomorphism with kernel I. And whatever this j bar is, it's an ideal, so it certainly contains 0. And so its inverse image contains the inverse image of 0, so it contains I. I'll let you check that it's an ideal. And to identify these two quotients, you just compose this homomorphism here with the extra quotient map from R bar to R bar mod J bar. So you take the composition of these two maps. This is another quotient. And the question is, what is the kernel of this composition map? Well, the first thing is that the composition map is surjective, because it's a composition of two surjective homomorphisms, both given by quotient rings. So it's surjective. With kernel, well, its kernel are the elements in R, such that when you map them to R mod I, they land in J bar. Correct? So that's exactly the things which are in F inverse of J bar. The things which are in R that map to J bar. So F inverse of J bar turns out to be J. I mean, you have to check that this thing, if you go around once, you get back to where you started. So this kernel equal F inverse of J bar, which is equal to J. And so, if you have a surjective homomorphism and you know its kernel, it identifies the quotient of this by the kernel with the image. And that's this. That's the proof of that.